In this video, we are going to talk about the derivative function. And if you remember from our previous video, we said the derivative is the limit as h approaches 0 of the difference quotient. And what's happening here is that we've got this function, and we're looking at 2 points along that function. And we're looking at what happens as the distance between these 2 points gets smaller and smaller and smaller. And we said the derivative gives us the slope of the tangent line. So we want that secant line to get closer to that tangent line, which is why we're looking at that limit as that distance between these 2 points gets approaches 0, so it gets smaller and smaller. So let's find the derivative of a few functions. We're going to start with this first one. We've got the function x squared minus 2x. So the derivative is going to be the limit as h approaches 0 of the difference quotient. So it's f of x plus h. So we're going to plug x plus h in for all the x's. And then we're going to subtract the original function because it says minus f of x. And all of that's over h. So let's simplify this. So this is going to be x squared plus 2xh plus h squared minus 2x minus 2h. And then we're going to distribute minus x squared plus 2x all over h. We're going to see some things cancel. Notice all the terms that we have left that did not cancel have an h in common. So we're going to factor it out. And then now you can see those h's cancel. The reason we want to factor that out is, remember, we want to take the limit as h goes to 0. This h in the bottom for this particular one is going to give us an issue because we cannot divide by 0. So that's why that cancellation is important there. So we have 2x plus h minus 2 left. And if we look at what happens as h goes to 0, we're going to approach the function 2x minus 2. So there's the derivative. And that derivative will give us the slope of the tangent line at any point along that graph. So since we know the derivative is the slope of the tangent line, we could use a picture of f of x to help us figure out what the picture of the derivative would look like. So we're going to have to analyze this. So remember, this derivative is the slope of the tangent line, and that's for f of x. So I'm going to start by finding horizontal tangents. Horizontal tangents are going to be places where the derivative would be equal to 0. So there's a couple of places here that derivative is going to be equal to 0. That derivative is going to be 0 at x equals 3. And then we have another one here at x equals negative 2. And then let's talk about where that function is increasing. So f of x is increasing between negative 2 and 3. Which means this function is positive. So we're going to have positive tangents. If we look at from 3 on, f is decreasing from x equals 3 to infinity. If it's decreasing, then all those tangent lines are going to be negative. We'll say they have negative tangents. or negative slopes. Over here to the left in -2, same thing. So let's think about what this positive and negative tangent line means. That's going to be the output for this. So what this means is if I get a negative tangent slope here and here, then that value of the derivative is going to be less than 0, which means the derivative is going to live below the x-axis. I wrote that in the wrong place. Let me move that down here because we were talking about the negatives. So likewise, if we have positive tangents like we do here, all those tangent lines are going to have a positive slope, then that means the value of the derivative is going to be positive, which means the graph is going to live above the x-axis. So we know that the graph of the derivative is going to cross the x-axis at 3 and -2. So 3 and -2. The question is it going to do this or is it going to do this? So we have to live above the x-axis between -3 and 2 because our outputs for the derivative are going to be positive. And then we're going to be below the x-axis to the left of -2 and to the right of 3. So our derivative is going to look something like this. Just a quick sketch. We found all of that information just by analyzing what that derivative is. It's important to make that connection between what f of x looks like and then what that derivative is going to look like. Let's do another one. Let's look at 13. We want to use the graph of f of x to sketch the graph of the derivative. So let's analyze it again. So we know we have horizontal tangents, which is where the derivative is equal to 0. Not 0 at, to me, this looks like it's probably about, I don't know, maybe 1.2. And then maybe -1.2 or -1.2, -1.5, -1 point something, and +1 point something. Now let's talk about where we have positive tangents. Positive tangents means that f of x is going to be, f prime of x is going to be positive. Negative tangents means the value of the derivative is negative. So we're going to have positive tangents up until this point because I'm increasing. So all those tangent lines are going to be positive. You could draw a few just to see them. And then we're decreasing, which means we have negative tangents. That's from -1.2 to 0. And then we increase again with positive tangents between 0 and 1.2. And then we have negative tangents on the right-hand side of 1.2. So let's plot what we know. I'm going to clean this graph up. Let's erase everything I have. We know we're going to have the derivative cross at 0, 1.2, and -1.2. So my derivative is going to be above the x-axis From negative infinity to negative 1.2, it's going to be above. And then from negative 1.2 to 0, it's going to be below. And then from 0 to 1.2, it's going to be above. But then 1.2 to infinity, it's going to be below. So there's a quick sketch of what that derivative would look like for that function. The next theorem is a really important one. It says let f of x be a function in a, b in its domain. F of x is differentiable at, if f of x is differentiable at a, then f is going to be continuous at a. Notice that order, if, then. If it's differentiable, then it's going to be continuous. It does not say if it's continuous, then it's differentiable. So differentiability implies continuity, but continuity does not imply differentiability. There are places where we have a continuous function where the derivative would not be defined. And those places would be things like sharp corners or cusps. And then any place we would have a vertical tangent. Next, two examples of that would be the absolute value of x. The absolute value of x is going to have an issue with differentiability at 0. And you can see that when you think about the value of the slopes here. My slope over here would be a -1, and this would be a +1. So at 0, it's, in a way, it's kind of confused because that left-hand limit and that right-hand limit is not going to be the same. So we would say that y is equal to the absolute value of x is not differentiable at 0. Everywhere else it would be fine, but notice that's happening at a sharp corner. Another example would be the cube root of x. The cube root of x is going to have an issue at 0 because we've got that vertical tangent line that could come out. And we'll see a little bit more of the y in upcoming sections. You'll see how it's an issue trying to plug 0 into that derivative, really for either of those functions. Did you know that you could take a derivative over and over and over, and that's called a higher order derivative? So we've talked about the first derivative. Let's talk about the second derivative. Notation for the second derivative is going to be f double prime of x, or we could say y double prime, or it would be d squared y over dx quantity squared. Okay, and where this comes from, we know the first derivative is dy over dx. That's one notation. And if we want to take the derivative again, you can see how if I were to just multiply the variables through there, we have dx quantity squared in the bottom, and that's what this is symbolizing there. Third derivative, you're going to see f triple prime, you're going to see y triple prime, or you would see d cubed y over dx cubed. Fourth derivative, you're going to start seeing that derivative notation in parentheses where you would expect an exponent. I have seen the fourth derivative written in terms of Roman numerals, but anything past that is going to use this notation here. So just to show you what the fifth derivative would look like, we would have f to the f to the fifth of x, or y to the fifth. That's showing that it's a derivative. not an exponent, that's because of the parentheses around it, or d5y over dx to the fifth. Either one of those would mean we have a derivative to the fourth order. So how would we find the second derivative? We just take the derivative of the first derivative. So let's find the first derivative. So to find the first derivative, we're going to take the limit as h goes to 0 of f of x plus h minus f of x divided by h. So we're going to square this out. When I square that, that's x squared plus 2xh plus h squared minus 3 times x plus h plus 1 minus 2x squared minus 3x plus 1 all over h. So this is going to be 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 1. And then I'm going to distribute that negative. And we're going to see some things cancel. The x squared terms cancel. The x terms cancel. And the number 1 is going to cancel with that negative 1. So we have the limit as h goes to 0. All of the terms left have an h in common. So I'm going to factor it out. And that's going to leave me with 4x minus 3. So there's my first derivative. And then now if we want to find the second derivative, we're going to take the derivative of the first derivative. So I'm going to take the limit as h goes to 0. Apply the difference quotient to this. This is 4x plus h minus 3. And we're going to subtract the original function all over h. Let's distribute. Cancel things. So we have the limit as h goes to 0 of 4h over h, which is the limit as h goes to 0 of 4, and that's just going to be a 4. So there's my value for the second derivative.